Ik open hier bij deze academische zitting waarin de heer Groot Lipman zijn academisch proefschrift in het openbaar zal verdedigen. Van nu af aan gaan we alles in het Engels doen, vanwege de gasten. Ik hoop dat het publiek dat ook acceptabel vindt. From now on, everything will be in English. Okay for you as well? Yes. And that is also easy for the ones I welcome now who are taking part by live stream. And everybody in the audience is also welcomed. Before we start our opposition, the candidate, the promovendus, will give a short presentation about his the research he performed and an overview of his research and a summary of his most important findings and conclusions. I ask you to start this presentation now and wish you the coming hour lots of success and inspiration.
Thank you. Dear Prorector, dear Corona, family, friends, colleagues, truly wonderful to see so many of you here today. In the next 10 to 15 minutes, I will present the findings of my thesis, Artificial Intelligence, the Key to Standardizing Respiratory Disease Evaluation. Imagine you've been coughing for a while. Not much out of the ordinary, but it doesn't get any better. You go to your local physician, and she is quite concerned, so she refers you for a CT scan. The CT scan comes in, and you're delighted to hear that the medical expert determines that there is no indication for a severe lung disease. Wonderful. However, for this suspected disease, 3 medical experts look at your CT scan, and the second and third do think there's severe lung disease. What is happening here? Do you have the disease or don't you? Often that's hard to say, because medical experts generally balance the certainty of their evaluation with the harm done to the patient. Then they can, for example, go into your lungs, extract some tissue to send to the lab, but it may do more harm than good. What I've been working on during my thesis is extracting more information out of these CT scans with artificial intelligence, or AI, to help medical experts make more consistent and accurate evaluations. In the first study, we looked at 509 patients that are suspected for asbestosis. And in the Netherlands, you can get financial compensation if you have asbestosis. Each of these patients had a CT scan and a lung function test to see how good their lungs are performing, and a verdict by 3 experts. If the majority of the experts think there's asbestosis, the patient gets financial compensation by our government. Now, 1 out of 4 patients gets such a mixed review where medical experts don't seem to agree, and we wanted to investigate this uncertainty. So we trained an AI model, basically based on a CT scan, to predict the outcome of the medical experts. We did this with 3 components. First, we had an AI model localizing the lungs, so the AI model only focused on what was important. Then we detected the abnormalities in this CT scan. And at last, we had a separate AI model predicting whether there was asbestosis. We showed that only on the CT scan we reached good performance. The AI was able to do this. But when we added the lung function test, it was even excellent. We came really close to the verdict of this panel. We also showed that we were able to distinguish these certain cases from the uncertain cases. And this is all great in a research setting, but you want to test it out in real life. Therefore, we did what we call a prospective evaluation. Every new patient that came in got the traditional evaluation, but also an AI evaluation. If the AI was certain, then that will be the final verdict, and it would classify as uncertain. 2 additional medical experts would help the AI out. Now, what was especially important here following the clinicians was that the AI wouldn't deny a patient financial compensation if humans would have awarded it. So, of all these 59 cases where the medical experts awarded the financial compensation, the AI should also have a really high number. And with some statistical measure, we determined that number should be 55. We did the prospective evaluation, but unfortunately, the AI detected 51 of these cases. But interestingly, that number didn't increase with the help of medical experts, because they often disagreed with each other or with the other experts on the other panel. We still showed a good performance of this AI model if we included all 92, also the negative cases. And this really shows that you can build a good AI model, it can perform well, even in these prospective validations, but that doesn't necessarily mean that it's also of added value. Because we were just able to have the clear-cut cases that the medical experts could already assign. What we could have improved is really focus on certain cases and basically making new criteria to help medical experts with these evaluations. The medical experts also spotted some thick layer around your lungs called pleural plaques. And unlike asbestosis, it is not yet known what the impact is of these pleural plaques on your lung function. If these pleural plaques make your lung function worse, so less air in your lungs, you may also be eligible for financial compensation. The research here is impeded by the fact that it's really hard to measure the volume of these pleural plaques. So we set out to make an accurate tool to determine the volume. Radiologists were so kind to provide labels. So they labeled every pixel in the CT scan that they considered pleural plaques, here in green. And we built an AI tool to replicate this. And we were quite successful. Here in yellow, the AI prediction. Now we can calculate the overlap between these two outlines, and we see how good the AI is doing. And we found a decent performance, 70% on most cases. And the volumes that were extracted from the AI and the radiologist correlated well, 90%. So with this tool, we are accurately able to determine the volume, and that will facilitate further research. As a use case for the patient of which we got the lung function test, we related it to the pleural plaque volume, and we found that a higher pleural plaque volume was related to a reduction in vital capacity, which is the total air you can exhale after a full inhalation, but not so much to the gas exchange in your lungs, so how much oxygen can transfer to your blood. We couldn't correct for confounders, thus it doesn't necessarily mean that pleural plaques are causing a reduction in lung function, but we make our AI model publicly available for all other researchers to extract this volume out of CT scans and do further research. In the next chapter, we performed an external validation. And what this means is that if you build an AI in a certain environment, you want to test it in another environment. So this was a commercially developed AI model that was built to label affected tissue of COVID-19. So here in yellow, you see how it labeled the affected tissue, and then it predicted the likelihood of COVID-19 present in the CT scan. Now we went to test it on 375 CT scans, and we found actually in our data set it was a substantial drop in performance. So the AI did worse on our set, and we deemed it not clinically sufficient to use in the clinics. Now this can have multiple reasons. The AI can just perform worse on these new cases, what often happen, but you also have annotation difference. So if the AI learned from a radiologist from the internal set, and now we test on annotations of a radiologist of our set, and these radiologists don't agree, that could also be a reason for this mixed performance. Because what we visually saw is that the AI wasn't particularly bad at segmenting this tissue, it was just conservative in relation to our radiologist. Then the last chapter, Artemis, where I by far spent most of my time on and are also most excited about, it's automated response evaluation to treatment in mesothelioma. And what is mesothelioma? It's basically the cancer version of these pleural plaques, a thick layer around the lungs. And it's very aggressive. 1 out of 2 patients dies within a year after diagnosis. So we want to be really sure that if we give treatment, that we can accurately determine if the treatment is working. Now, how do we do that normally for all other tumors? Let's consider this circle to be a tumor of the first CT scan. We measure the diameter. Then we give treatment, wait 6 weeks, and we measure the diameter at the same location again. If it grows by more than 20%, we have to stop treatment. It's progressive disease. Treatment didn't work. Less than 30% shrinkage means treatment is really working, continue, and everything in between is stable disease. This might work reasonably well for spherical tumors that are round, but not all tumors are the same. And in mesothelioma, you really have to choose a location along this layer of tumor where you're going to measure. And as a mental question to the audience, you have to choose now on baseline where you're going to measure in green, red, or blue. Then we give treatment, wait 6 weeks, make another CT scan. Now, if you chose green or red, the patient has to stop treatment because at those diameters it grew substantially. Well, at the blue, not so much, and you could actually continue. This is just for illustration purposes, but in a recent clinical trial, which is very controlled, 2 experts in the field only agreed in 53% on a classification on how this patient was responding to therapy. And we really have to do better for these patients. So we set out to extend the pleuroplaque project and extend it to do a volume assessment automatically of mesothelioma. We did it much bigger. In total, 11 medical experts annotated a lot of these 2D slices, more than 100,000 in total over these CT scans. We trained across 16 hospitals and reached excellent overlap, so our AI was really able to accurately determine the volume of this tumor in these CT scans. Then I went to Zurich to perform my own external validation on their dataset, and we actually found quite a low overlap with the manual annotations of the radiologist. And I sat down with her, and we went through the case, and she said, the AI might be better than my annotations. And to test this hypothesis, we set up a blinded study where 2 new radiologists would get all these 22 CT scans. We showed them both segmentations, and they had to choose which one they prefer. And what we found is that the AI segmentation was preferred in 70% of the time. Just, visually speaking, outperforming the radiologist. And 16% they were neutral. Now, this is good to show that the AI wasn't doing a poor job on the external validation set, but what we rather should be doing is not AI versus the human, but how can humans leverage AI to get the maximum out of these CT scans? So in the next external validation, across 24 hospitals in Europe, we predicted with the AI thousands of CT scans, selected 200 of them, and then we make an AI prediction. So the AI is first to make this prediction, and now we ask a radiologist, hey, can you show me where the AI is wrong? And then they can have modifications, so we get the final tumor volume. And this turned out to be really successful. So we only needed minor modifications. We reached a 98% overlap, and only in 5 of these cases, the radiologist really had to significantly adjust the tumor. I've been showing you the entire time these 2D slices, but actually CT scans are 3D, so there can be hundreds of these slices throughout one CT scan. And if we visualize the segmentation of the AI, so the labeling of the eye in 3D, you can see here the 3D model of the entire tumor. And I hope you can appreciate how complex the shape of this tumor is, and that we cannot really measure it accurately with simple diameters. So left, we will iterate over all slices. You see how this relates to 3D. And this is just an illustration of one patient, but we've run this analysis now for thousands of patients. And what we can automatically visualize is here for 4 CT scans of one patient, each with 6 weeks in between, we can monitor the tumor growth. And what you can see already in the 3D model is that over here, the tumor grew massively. I think there's no doubt about it. The question here is what is happening between CT2 and CT3. Was there already enough growth of the tumor to stop treatment? And we found that with simple measurements for this case, but for many more cases, the diameter measurement stayed stable, but we already detected automatically that there was a huge increase in tumor volume. And it actually, in hindsight, it would have been better to stop treatment there or switch treatment. And which is confirmed by the next CT scan when it's actually already too late. We crafted these new criteria to automatically determine when you should stop treatment. and we will propose this in a future publication. To conclude this chapter, we are able to automatically and accurately determine the tumor volume on these CT scans. We have shown that it has a better relation to survival with our new criteria. And with our new criteria and this automatic volume, we can detect ineffective treatment 7 weeks earlier than the traditional methods. I really hope and do believe this will be the future of patient care in mesothelioma. I want to thank you for your attention and give the word back to the prorector.
Thank you for this presentation, which gives us a reasonable view over your research. And for me, at least, it makes it all more understandable, I hope. We have had a problem with contacting one of the opponents, and I don't see her yet on the screen, so I have to...
She is there, I think.
Yeah, that is Professor Lambert.
Yeah, but beneath it is
Professor Kool. Professor Kool also here?
Yes.
Okay, then we have all the whole board together. Then that means that we have 1, 2, 3, 4, 5, 6 opponents. And that means that for the people who want to follow us, about 7.5 minutes for each of them. Oh yeah, Professor Kool, welcome. Just in time. We have started, we have had a presentation by the candidate. We have decided to do everything in English. I hope you agree as well. And then we go now to the group of opponents and start with Professor Fransen. He's a pulmonologist at our university. He's sitting over there, and he was the chairman of the Manuscript Assessment Committee. Professor Fransen.
Thank you, Mr. Prorector, dear candidate. First of all, congratulations on your thesis and the way you presented it. I really enjoyed reading your work, and it got me thinking of a lot, and I only have a few minutes of time. Also, congratulations to your team. So, before we go look inside your thesis, I would like to focus on the outside, and not on the image, but on the title of your thesis. Because when I first noticed it, I thought, this is really going to change my work, because you say we are going to standardize respiratory disease evaluation. But then I was a little bit disappointed, because the diseases you focus on, asbestosis, I think 30 new patients every year in the Netherlands, mesothelioma, maybe 1,000. The number of patients with COVID-19 that get a CT scan is only maybe the 5% of those hospitalized. So I don't think it's actually respiratory disease evaluation, but I would like to know what your opinion is, and should you maybe need to choose another title for your thesis?
Highly esteemed opponent, thank you for your kind words and intriguing question. That's an interesting take, and I think in research we never solve all problems at once. First we have to develop methods and show it on smaller populations before we can transfer them to the bigger one. I do agree this thesis is not going to solve the biggest respiratory diseases, but I think there are certainly methods that can transfer to the more common diseases. So to conclude the title, no, we are not going to solve all respiratory diseases or your work for most of the patients.
Can you speculate on how you can translate the results to more common diseases, for example, like COPD or asthma?
Yes, we focus mostly on restrictive diseases like asbestosis. To my best understanding, COPD and asthma are both obstructive diseases. They will have different features in the CT, but definitely I think for asthma and COPD, the problem is the exhaling of the air. So if we can make CT scans at multiple time points, for example, I would hypothesize that AI would be able to detect that and really benefit those evaluations as well.
Okay, thanks. Then you're in my clinic now. I have clinic tomorrow afternoon, and imagine a man comes in, he's 60 years old, he's smiling, and he says, well, I come to collect my money because I was exposed to asbestos for more than 20 fiber years, how you call this?
Yeah.
So what would you do with your respiratory disease evaluation?
Well, it's a bit tricky because it's no longer only the clinical diagnosis, but it's also a legal diagnosis if we want to give financial compensation. So we have this official framework where following a GP or with a CT scan, you go to the Institute of Asbestos Victims and they ask medical experts to look at these CT
But
scans.
what is the first thing you would do? You're a clinician, right? You said
Yes.
Yeah, so what would you do?
I would recommend them to submit a financial application.
No, but before that.
So two things. You have the clinical thing and what we discuss in the thesis.
Yeah.
For the clinical, if they come into clinics, I would do like inspection of the body, do a lung function test, talk to the patient, ask them for more of their symptoms.
Yes, and that is something I miss in your thesis, because in my view, asbestosis first needs to be a clinical diagnosis, with a person having symptoms and having maybe signs on physical examination. But I was just wondering, because you focus so much on lung function, on CT scan, and on exposure, but you never in your thesis, except for chapter 3, you mentioned symptoms. But I was just wondering, what about symptoms in your population? Do they have symptoms?
We are not sure, because we get this information through the Institute of Asbestos Victims, and we cannot, that's also what hinders the evaluation of the lung function in the chapter of the pleural plaques, that we cannot go all the way back to these patients. So we don't even know the physicians that treat them on a daily basis. So we do our analysis after that point of the symptoms. And I fully agree these symptoms are very important, but our research is focused on the part after this. And then.
But should you not take symptoms into account in your modeling?
You could, but that has been demonstrated to be very difficult, because symptoms are mostly subjective. With recent advances, I think it's possible. If I would now start my PhD thesis, I think with large language models we can analyze all these reports of clinicians with patients and then filter out these symptoms.
Yeah, because I was a bit intrigued by, you say there's a lot of disagreement between pulmonary physicians, but that's probably related to the fact that there are other factors that can be responsible for this low lung function or for these.
Yes, and the fact, like you said, that they don't get to see the patient. So they only get to see the CT scan and the lung function test and the asbestos history, but not the real patient.
Okay. I have a minute left, I guess. I would like to focus on the finding in chapter 4, where you say the subjects have a low forced vital capacity. And you say, well, that is probably the result of restriction, which is the result of fibrosis due to the exposure.
Yes.
Can you think of another reason why these subjects would have a low FVC? And I'm trying to relate that to the fact that most of the subjects in your thesis were also smokers.
Yes, so I think, as we also discuss in the paper, there are a lot of external factors that aren't known to us, BMI, smoking, that can definitely affect the FVC. So it's not only the restrictive lung disease of the asbestosis, but those were unknown to us. And therefore we're really careful with not calling it that pleural plaques are causing a reduction in FVC, but only a relation. They're correlated.
Mm-hmm. Do you know how smoking is related to a lower FVC?
Not particularly, but if I could reason, I would say they make also some kind of scarring of this nicotine is causing the FVC to drop by ensuring that the lungs cannot fully stretch. So you cannot exhale all the air that the normal lungs would be able to do.
Okay, that's a good attempt. I'd like to give the word back to the pro-rector, and I hope maybe we can have some discussion afterwards.
Of course.
Thank you, Professor Fransen. Then we continue the opposition by Professor André Dekker. He's a professor in clinical data science at this university. He was a member of the assessment committee of the manuscript, and today is acting as the secretary of this board. Professor Dekker.
Thank you, Mr. Pro-Rector. And the candidates, also congratulations on my behalf on this lovely thesis, which I enjoyed very much reading. I would like to ask, while you drink some water, to read proposition number 6.
A gold standard, specifically in medicine, does not mean it's good nor objective. It is merely the best we currently have under reasonable constraints, and we should question its relevance with more skepticism.
Thank you. So in chapter 5, I was surprised when I compared the statement to something that you mentioned on page 95, which I will read to you, which is the datasets consist of patients, about 1,000 T-scans, with available RT-PCR test results for COVID-19. So then I'm reading on, I'm thinking, oh, we're going to see if a CT scan can be used to detect if a patient has COVID. But to my surprise, you're not doing that. You're correlating that CT scan with some intermediate thing done by a so-called expert called CORADs. So why did you choose CORADs and not just the diagnosis of COVID?
That's a very valid concern, and I exactly the same concern. The problem with that chapter is that we were asked to do an external validation of a model that was already developed and developed to predict CORADs. But from the get-go, together with Lawrence, my co-author, we said it doesn't make much sense, because if you have the RT-PCR and you have the CT scan, just predict the COVID diagnosis directly. But we were kind of forced to evaluate it this way because they already had trained the AI model that way. So I fully agree.
Okay, thank you. Now, we did the same at Clinical Data Science. We got a model out of China, the Wuhan, where the pandemic started, obviously. And they made a model on 5,000 CT scans there to detect COVID directly, right? Because CORADs wasn't there yet. And they sent it to us and says, here, you use it in Maastricht, right? So we got it for free for them. And in Maastricht at that time, we had a bus parked in front of the hospital where people had to get a CT before they went to the hospital. And there was a radiologist checking whether the patient had COVID or not. So when we validated that AI algorithm from Wuhan, we found more or less the same as you. It didn't work at all. The AUC was about 0.5 for COVID. So why do you think that is?
I think these AI models have been developed of very specific data sets that are highly curated. And if you test them on...
Well, there were 5,000 patients in Wuhan. They were not curated. They were just pumping out of the hospital, right? So it was not a curated set. It was their clinical set.
And they all had COVID or all suspected patients?
Well, they had a bunch with COVID, so they did the RT-PCR afterwards. So they had confirmation of a test, yeah.
So what you see in these COVID periods, that if you have a high prevalence in certain periods and you train on a data set from that time, the AI model also learns the underlying distribution of those CT scans. Mm-hmm. So it could overdiagnose. Another factor of external validations is that patients over here have a different anatomy. Mm-hmm. So it doesn't generalize. It was very specific for Chinese patients. And then you see on some kind of feature that, for example, Dutch patients have, it triggers and then it predicts accordingly.
That's certainly the case. However, I was also surprised by your table 5, which had all these hospitals that supply data. Now, my guess is all these hospitals have different CT scanners.
Yes.
Right? And there were some Singapore patients as well, I see. From LifeTrack. But you don't mention that in your thesis, right? So you do some DICOM standardization, if you want, right? I think you're doing some slice or isotropic voxels, or at least similar voxels. Do you think that's sufficient for AI to just use any CT scan?
The current literature doesn't seem to support that. So we have these high variances. I think we should train AI models that are invariant to that shift. So I think definitely it is possible, but it has barely been done yet.
And how would you suggest to do that then?
You could do it in different ways. I think the most likely way we were able to achieve is if we have a large collection of, let's say, hundreds, if not thousands of hospitals coming together and pre-train an image encoder on millions, if not billions of CT scans.
And how would you go about that?
That's a good question. Well, my professor has recently started UCAME already for a Europe consortium to get all the CT scans together. Okay. And in the States, you can actually buy CT scans. So they have these big databases you can buy. So
Yeah.
I'm definitely willing to try that out, yeah.
Okay, that's good to hear. Because I think it's quite important to have the AI learn differences between scanners and then see if we can normalize scans before we do this kind of stuff.
I think so
Thank
too,
you
yeah.
for your answer. I give
Thank
the
you.
word back to the prorector.
Thank you, Professor Dekker. Then is Professor Kool, who is now taking the discussion over. And you were not with our pre-discussion. You remember that you remind that you have 7 minutes and a half about for your discussion. Professor Kool, she's head of the radiology department of Aachen University, and she was also a member of the assessment committee of the manuscript. Professor Kool.
Thank you very much for giving me the opportunity to participate in this prestigious event, and congratulations to thesis that it was exceptionally well written, and I think dealt with a clinical problem of relevance to current clinical medicine. So, but my role here is that of an opponent, and therefore I would like to ask at least 2 questions. My first question relates to the same chapter that was just discussed, the one on using AI to use COVID or diagnose COVID-19. As you know, most of the algorithms that have been trained were trained on data sets of early viral victims, but the viral variants have changed since then, and with that change, also the imaging appearance of COVID-19 pneumonia has changed. How does your algorithm account for this?
Thank you for your question. I think the AI model doesn't, and that's a big problem. And I think the COVID-19 pandemic showed us as no other is that we all rushed to develop these AI models, but when the pandemic evolves, then we found out that you have these long-term effects of COVID, and that really affects the AI performance. And then you see these drops in external or prospective validation. But that's hard, because you don't know, especially for a new disease, how it's going to develop and what the effect on the CT scan is going to be.
Right, you never know how the virus develops, but do you have any plans, or would you have any suggestion on how to deal with this problem? Would it make sense, for instance, to collect CT scans of patients admitted with known COVID to check whether the imaging phenotype of COVID-related pneumonia changes, and then adjust your algorithm, or do you have any other suggestions to deal with this problem?
Yes, so I have some thoughts about how solving this. I was just also discussing with Professor Dekker that I think these large models that are pre-trained on millions of CT scans, if you can get powerful feature representations out of these CT scans, you can measure this data drift, basically. So of all the CT scans of now, of early COVID period, you store all these feature factors in a database. And then as COVID develops, you check for each CT scan if it's still in the distribution of those previously known CT scans. And if you can detect some drift, then you know something is up and you have to investigate.
Okay. Did you ever consider using an automated AI analysis for more epidemiological purposes? I mean, if you have an AI algorithm that assume it is predictive of COVID-19, would it be possible to use this for an automatic analysis of all chest CT studies that are being done in your country for whatever reason, to get some sort of epidemiological signal, so to speak, in case there is another upcoming viral variant or epidemiological drift towards a higher incidence of COVID?
I think we could, definitely. I'm not sure how useful it will be to do that on CT, because if the patient already has to come in with symptoms and everything, and then you make a CT, I think you're already too late. So if you would do that, I would do such an AI analysis on some data that's more preventative. I think they do something with the water in the sewer now, that you check the values. I think that you are then before the pandemic happens instead of afterwards thinking about what the numbers are going to be.
That's certainly correct. Then another question is, many patients who undergo CT imaging, at least in the early days, the question when there were no antigen tests available, and we indeed, just as you, use CT imaging to diagnose affected individuals. How does your algorithm deal with the fact that patients who do have coughing and sneezing may have viral infections that are non-COVID related? I mean, how good is the distinction between COVID-related pneumonia and non-COVID-related pneumonia?
Yeah, not good at all. So we saw that with the CORAD's score prediction that these models for pneumonia or other benign diseases, that it gave a very high CORAD score, while the radiologist thought it was a very low CORAD score.
Yeah. So the problem is that you will use that system, or that we could have used. We deal with an algorithm that enables early diagnosis of a disease that doesn't exist anymore. But in the time when it existed, it was not overly useful, simply because of the fact that people who did have clinical symptoms often do have other causes of pneumonia rather than COVID. So that is another problem I think people have to deal with in future pandemics. How did you, in the current data set that you use, how many patients did have pneumonias other than SARS-CoV-2?
I wouldn't know on the top of my head. I would have to investigate.
Okay, good. So, Mr. Prorector, these were all my questions. Thank you.
Thank you.
And congratulations. Yeah.
Thank you.
Thank you, Professor Kool. Then we go to Dr. Thewen. He is head of the Oncology Data Group in Antonie van Leeuwenhoek ziekenhuis at Nederlands Kankerinstituut. He's also attached to the University of Amsterdam, and he was a member of the Manuscript Assessment Committee. Dr. Jonas Thewen. Dr. Thewen. There he is.
Thank you, Mr. Prorector. Dear candidate, I want to congratulate with your thesis. There's 6 papers. I have not seen many theses with 6 AI papers, so that's kind of that's very impressive. Actually, I would also like to start with the cover of your thesis, because somewhere you write this is done by GPT-4. So first, what's the query? The lungs are Amazon forest?
Yes, that's how it started. I think esteemed opponent, thank you for your kind words and your question. Yes, multiple iterations. I've had, I think, 4 versions of the cover, printed as well. Colleagues and girlfriend has to evaluate it, and then we improved.
So this is directly from the model?
Sorry?
This is directly the model output?
The front cover is, and we tweaked it with some own adjustments. Yeah.
Okay, great. Good to know. Because GPT-4 is a foundational model, as we call them, and so we seem to be very intrigued by them. And I also know you're very intrigued by them, so we will ask you questions about that. And in particular, connected to proposition 2. Could you please read that?
In tumor response evaluation, consistency in measurement over time points is of utmost importance.
Maybe it's good if you give a 1-sentence explanation of what a foundation model is, but how does this statement work in the context of foundational models? Because you mentioned measurement. What does that even mean in the context of foundational model?
That's a very good question. The first question...
So, sir, please also answer, it's of utmost importance if that still holds in the context of foundation models.
All right, I think we are discussing 2 different things here. First, foundational models, for example, trained on a massive set of millions, billions CT scan, mainly in a self-supervised manner, so you don't need any labels. ChatGPT is the most famous example, but for images we can make also foundational models. And what's important is pre-trained on a lot of data, and then you can do downstream tasks. So if you want to segment mesothelioma or classify COVID, you can do it all with that foundational model. Second, the measurement, I define it quite broadly, but in the context of our thesis, let's take mesothelioma, the medical expert still has to correct these volumes. And what we don't want to have is that, suppose you are in doubt whether it's atelectasis, a benign structure, or tumor. On the baseline, the radiologist decides to include it, and then another radiologist on the follow-up scan excludes it. And then you get this artificial drop in your tumor in your volume. And therefore, I mean, it's of utmost importance that we keep that
All right. That's
consistent. Yeah.
Okay, that I understand. But in the whole AI field, the point is probably to take your image and predict a clinically relevant outcome. Now you're predicting something intermediate, which requires like 11 annotators or something you have mentioned. So how would you actually see basically part 2 of your thesis, your most important part, in the context of foundation models? Do we need all these segmentations?
That's a very good question. I'm not sure how the field is going to develop, but we can do 2 things. We keep on measuring this in CT scans and get these volumes like I've presented in part 2, or we can directly predict from the images if there is progression. I think the latter one would be more interesting from a methodological perspective or a technical one, but I don't think from a clinical perspective that makes much sense, because then you get this computer says no idea when an AI says, all right, this is progression. You don't know why, you don't know how. So I think this intermediate step is very important for clinical application.
All right. I don't think I agree with that, because you've also mentioned the word large language model.
Mm-hmm.
So how do you see, I could imagine that a large language model could be useful to help you with that problem.
Yeah, for sure. From a technical perspective, I think it's definitely possible, and we can build such a system if we get a really good team and a lot of data. But from a patient or a doctor's perspective, if such a gigantic model determines something that it cannot explain or cannot express in
LLMs can do
volumes.
this, right?
Yeah, but LLMs can also hallucinate, so they can trick you in believing something. And then here, we don't have much of a zoo culture, but especially in America, you would have a big problem, I assume.
Okay. So basically, you say we don't have to throw your thesis out of...
Not
yet.
I think foundational models are going to help Artemis as well by pre-training on a... Because what the current model is enabled to do is take into consideration the prior adjustment of the radiologist. So let's consider it makes a big mistake on the first CT scan. Radiologist, all right, let me correct it. But if the CT scan doesn't change in 6 weeks, it will make exactly the same mistake. I think foundational models will help us here, where we can train a model not only to consider the current CT scan, but also the prior CT scan with the adjustment made by the radiologist. And the big advantage here is that you don't have to retrain. And from a regulation point of view, that's very important, because we cannot retrain on all these corrections of the radiologist, because we have to go through the regulation again.
All right. I would have hoped you would be more positive about foundation models, but I'll
I am in certain cases.
Okay, then I would like to continue with proposition 9. Could you please read that?
Sooner than later, AI will be consistently outperforming humans, and we should have novel evaluation methods in place to assess superhuman performances.
Thank you. Could you explain this a little bit better? I suppose you mean you relate this to the segmentation outputs.
Yes, in the context of the thesis, I do. Yeah.
Okay. So how do you see that how would you see that progressing? Do you have any suggestion on how to approach this problem?
I think the way we solved it currently with this blinded study is interesting, and it gives you some kind of context of which is performing better. But you can also relate it to, for example, having manual segmentations and those volumes, and you relate them to clinical outcomes. So, for example, to survival, and you make these Cox proportional hazard methods to show that it relates better.
That's a good point, because now you mentioned cox survival as an outcome. I would assume that's a better, more relevant to the patient than their tumor volume is. So don't you think that we should evaluate based on those principles, especially in the context of the foundation models?
We could, but I think not particularly for the patient, but on a population level. We have to be very careful that these don't really mean much for the individual patient, but on a population level, we can split different groups that have different outcomes, yes.
I would be able to discuss for way longer with you, but I will return the word to the prorector.
Thank you so much.
Thank you, Dr. Thewen. Then we continue the opposition by Dr. Van Geffen. He's a pulmonologist at the Medisch Centrum Twente. No, not Twente, sorry, Leeuwarden. That is even more north. And he was not a member of the assessment committee, so he's quite fresh to this booklet. Dr. Van Geffen.
Mr. Candidate, congratulations to your thesis. Also, congratulations to your team. I've read it with lots of interest. It contains basically everything on a technical perspective, what I love as a pulmonologist: acute COVID, thoracic oncology, AI. So it was a delight to read it and to be able to discuss this thesis with you today. I would like to start about chapter 6, the Artemis. You said it was the project I worked on the most, and you're very ambitious there, because I think you're trying to address one of the most difficult things in thoracic oncology, basically the assessment of the CT scan in mesothelioma. You're so ambitious that you even try to assess not just one scan, which is already difficult for us as a pulmonologist, but also rows and continuous ones. And I was wondering, when you were building the model, how did you address the fact that we humans, and we are pulmonologists and radiologists, are very bad basically at addressing what is a tumor and what is not, and especially on the chest invasion part of that, because I think that could be very difficult.
Esteemed opponent, thank you for your kind words and your intriguing question. I agree, it's a very good one, and it's a very difficult problem to solve. The way we did it is that you want to have as many high-quality annotations over as many samples as you can get. So we had this AI assistant pipeline, where first a group of 4 radiologists recorrected basically the AI, and then we had an expert thoracic radiologist even correcting the other radiologist. And we see that AI, if you train on, let's say, 50 samples, it will perform quite badly, but it generalizes if you increase the number. So when we reached that 300, 400 number, it found a solution to be consistent. That said, I think we don't have to be perfect on the single scan, but we have to be consistent over multiple scans. Because clinically speaking, especially for clinical trials, you're interested in the effect of the treatment on the tumor. So whether on the first scan this is 700 milliliters or 750, it doesn't really matter that much if the change is consistent.
All right. But still, we at the beginning have just one scan when the patient got his diagnosis. So for us, the clinical part, it's very important to see and to correctly assess this first scan. And I agree that multiple scans are very important later. When we go to this first scan, well, as a pulmonologist, I'm very able to make a small assessment about the CT scan. And I would have hoped that the AI system, which is very sophisticated in the Artemis criteria that you also discuss in this thesis, categorized the basic scan with a tumor mass which is basically low, medium, high, or very extensive. And well, I had hoped that that would be a continuous value there, and only this categorization was relevant on the prognosis, if I read it correctly. Why did you choose these rather subjective human outcome measurements there?
Excellent question. The sole purpose of that categorization was for illustration purposes. So we have, because we heard from oncology, but we have T-staging. T-staging has 4 stages. So even with very arbitrary cutoffs, it was like every 250 cc's, we showed that it's much more prognostic than T-staging. We are currently investigating these fine-tuned, basically, cutoffs. So we do have cutoffs, but in generally, you could do it also continuously and then get a prognostic value for this patient. I think it is important to have categories, even if they're quite suboptimal, so you can really, or easily also for oncologists, compare different trials of mesothelioma, which is currently very hard.
It is, but still it's a very impressive technique, but there's still a lot of work has to be done. When I want to use it in my clinic, and I think I read it correctly that it's already implemented in the NKI, what are the steps you need to take before this model can be implemented in, not Twente, but Leeuwarden?
That's a good question. It depends on your infrastructure, because we are currently in a collaboration with a startup to build this entire infrastructure that automatically checks for every CT scan that is made in our EPD whether this patient had mesothelioma, and then the CT scan is forwarded to our AI model that runs in the cloud, and this volume comes back. We still have to get MDR clearance, the regulatory. We are close, and then we can use it in our hospital. But we use this exemption in the MDR. Before we have it to Leeuwarden, then we need to go to the European Union and get official approval. I'm afraid it can take years.
I'm sure it will take, but I look forward to it. Do we have time for one more question?
But that will be detrimental to the position of Professor Lambert after you.
All right. Then I give the word back.
Thank you.
Then is, as I said, the opposition to Professor Lambert. When I was still working, he was a radiotherapist, but now I read here that he has a chair in precision medicine. Is Professor Lambert, yeah, can you show him a bit enlarged on the screen? Technicians, please. Yeah, no, you don't have to do anything. I hope that the CT people do something with you and replace Professor Kool by your... No, yeah, there you are, Professor Lambert.
Yes. So, dear candidate, compliments and felicitations to you and the team for this very comprehensive thesis. My first questions will be to the response evaluations of mesothelioma, which I like very much. So one of the challenges of immunotherapy is that we can have pseudo-progressions and then wrongly stop or stop too early a patient that could later on respond. So you didn't discuss that too much in your thesis. Could you tell me a little bit more? Have you seen cases of pseudo-progressions?
Highly esteemed opponent, thank you for your kind words and your very interesting question. This is currently a hot topic in our group for investigation. We looked into it and now already quite extensively, and we thought we saw a lot of pseudo-progression, but in hindsight, I don't think it happens that much. So what is, for example, happening if a patient, let's consider, have a 200 cc volume, it doubles every 6 weeks, so 400, and now we start measuring. So this is what we call the baseline. The next scan is 450 cc, so it still grew, but by much less than you would expect following this exponential growth. So there is already some effect of the treatment, but because it was larger in volume than baseline, we call it pseudo-progression, because afterwards the treatment is working on full force and it dropped down to 300 cc's, let's say again. That said, we definitely saw a few cases of pseudo-progression, and that's why we also recommend the term unconfirmed PD. So in these cases, wait an extra scan.
All right, but do you think, if you check in the literature, are there methods eventually to diagnose this very early on, a case that could be a pseudo-progression and for which you don't have to stop the treatment? Have you seen anything there in the literature?
DNA is the most promising one.
Excuse me?
DNA. So circulating tumor DNA in the
Right.
blood.
By using imaging, by using AIs for imaging, is there any method you think to diagnose pseudo-progressions based on, for example, texture changes?
I think that will be extremely hard, and we will need the help of AI models there. because I think on visual inspection it's extremely hard to distinguish pseudo-progression from real progression.
Okay. So my next question is about explainability, interpretability. You said earlier on that's very important, but surprisingly in your thesis you don't say a lot about it. You just use saliency map. Could you tell me a little bit more about, are there some more advanced methods to bring more information about explainability of AI models?
Yes, of course. I think it's very important to define when we would need it. And for the case in Artemis, I don't actually think we need that much of an explainable AI model, because it outputs a segmentation mask that medical experts can verify, adjust, and then confirm. So they are then responsible for the volume. They can always be checked, so we don't really need the AI to be explainable how it got that segmentation. If it consistently performs well, that would be good enough. Now, this would be different if we would train an AI model, for example, on the baseline, and we are going to predict what treatment we should give the patient. Then we need a highly explainable model. The exact ways, there's a lot of research going on. You can have counterfactuals, for example, that you generate different images. I don't really longer trust saliency maps in light of new evidence over the past few years. Well, I did publish that a few years ago in that paper. I don't think that's the explainable method to use.
Okay. Yes, I also trust a little bit saliency maps. Have you compared different algorithms?
Could you repeat it?
Have you ever compared different algorithms producing activation maps?
Yes, for the saliency maps we did in a chapter of the asbestosis, we had these 4 different models with and without anomaly heat map, and we compared them. They were actually relatively similar, but this is really hard to quantify, right? And I just did it on visual inspection, so no quantitative analysis was done on the explainability or the saliency maps.
Okay, because our experience is that there is a big diversity between the algorithms creating activation map.
These algorithms were trained on the same data set. Yeah.
Yes. So when we use this different algorithm on the same data set, we often see different results. So we don't trust them neither. Yes. All right. And in the field of explainability, have you ever worked on latent space? Can you tell us something about latent space?
Sorry, I couldn't hear you correctly. What's the...
Have you ever worked with latent space?
Latent space. Yeah, we have. Yes, we have investigated latent space, especially in the variational autoencoder in the chapter of asbestosis to generate these heat maps, where we actually investigated the latent space a lot.
Okay. Right, and perhaps the last question. So in your COVID data, you had some difficulties to reproduce the initial results. Do you think that improvement in the post-processing or pre-processing harmonization could help there?
Yes, but only for the centers that you then include. I think that's the problem also with harmonization. That you have to be very careful of what centers you include and what patient population you have.
Okay, right. I thank you very much, and I give the word back to the prorector.
Thank you.
Thank you, Professor Lambert. And as you have noticed, the time for the defense of your thesis has passed. The committee will withdraw for its evaluation, and we will. I ask you and your company to stay in this hall until we return with the result of our deliberations.
Thank you.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. All your time, cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Get the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. Southside, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goals only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and die. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
has decided to grant you the doctor's title. Your Professor Regina Beets-Tan is authorized to confer upon you this distinction.
Please try again and use the microphone.
The floor is to your promoter.
Thank you.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you Kevin Bernardus Wilhelmus Groot Lipman, the degree of doctor, and grant you all rights attached by custom and law. And as evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the University of Maastricht. Certificates. Standing ovation from your family and friends, and you deserve it. Congratulations, Kevin. And it is my honor, because it was not only me as supervisors, but the excellent supervising team. And it is my honor to give the microphone who will honor you, and we will do that in Dutch. The clinician, the most important, our thoracic doctor, Dr. Sjaak Burgers.
Dank u wel. Wel edelzeer geleerde heer Groot Lipman. Geachte dokter. Beste Kevin, hartelijk gefeliciteerd met deze mooie titel, met je prachtig proefschrift. Je bent al een paar keer gefeliciteerd en heel graag wil ik die felicitaties me daaraan toevoegen. En ik wil ook graag je partner Kelly, je ouders, je familie en al je vrienden hierbij feliciteren. Je schrijft al zelf in je dankwoord, dat hoef ik niet te verzinnen, dat het zonder hun ruggensteun en zonder de rust die je thuis daarvoor door hun krijgt, dit nooit had kunnen redden. En graag benadruk ik natuurlijk dat deze felicitaties gedeeld worden door je promotor, professor Beets-Tan, en door Stefano Terbeschi. Hele eer dat ik namens hun mag praten. Eigenlijk heb je 2 weken geleden al een laudatio gehad. Je ging naar professor Beets-Tan om je arbeidsvoorwaarden voor je komende aanstelling te bespreken. En spontaan kwam er een fantastische laudatio. Ik denk, waar moet het over? Ja, natuurlijk. Deze mensen waren niet bij je loonsonderhandelingen. We gaan het nog een keer overdoen. Je begon ons instituut als masterstudent. Zo rond 2020 ronde je dat af. En ik heb nog nooit zo'n prachtig boekje gezien als afronding van een studentenstage. Het was bijna al een promotie, een thesis. Het was al goed, maar het werd steeds beter. En ik ben heel blij dat ik die groei die je hebt doorgemaakt mee heb mogen maken. Het gaf heel veel plezier. En dat plezier dat bestaat door een heel erg groot deel. Het werkplezier, jouw werkplezier, wat heel erg besmettelijk is als je bij je in de buurt komt. En ik denk dat het daar een beetje om draait. Dat wil ik graag uitleggen. De eerste studies die je deed, die focusten op al die CT-scan-evaluaties. Duizenden CT-scans, je zei het al, 100.000 koepers die ingetekend moesten worden. Dat was een hele hoge verwachting die daarvoor een gewoon studentje werd neergelegd. Dat gewone studentje, dat moest de gevestigde orde van de radiologen overtuigen om mee te werken en al dat werk te doen. Al die uren te investeren. Nou, die mensen die waren blijkbaar vatbaar voor jouw werkpleziervirus. Je hebt ze fantastisch overtuigd. Het helpt ook dat je goed naar ze luisterde en iedere keer weer teruggaf wat ze vroegen. En ja, je streelt iemands eer als je merkt of laat merken dat je naar ze luistert. Erg goed gedaan. Dat toegevoegd aan het werkplezier, wat kan er misgaan, hè? Datzelfde werkplezier, dat heb je vervolgens, toen we al het werk in ons eigen ziekenhuis hadden gedaan, in ons eigen instituut, vertaald naar het werk in de grote wereld. Je ging internationaal de boer op, mocht met je mee naar het Mesothelioma-congres in Lille, Frankrijk, niet zo ver weg, maar erg leuk. En daar heb ik gezien dat datzelfde werkplezier besmettelijk was voor al die grote internationale gevestigde orden. Moet ik zeggen, die mannen en vrouwen, de mannen en vrouwen, waren vaak wel een beetje jaloers als je vertelde wat je allemaal al had bereikt. En ze wilden graag meedoen. Ik heb ze hier, toppers uit Engeland, Schotland, Verenigde Staten, Australië, Europese organisaties als de ETOP, coördinatoren van grote internationale studies. Ze sloten aan achter in de rij om met jou mee te mogen werken. Indrukwekkend. En dan laat je een andere kwaliteit van jezelf zien. Wil je meewerken, moet je goed zijn en snel, anders niet. Ja? Zo werkt het. Maakt niet uit of je naam nu staat of niet internationaal. Ja, dan ben je internationaal en dan krijg je daar de aandacht en de eer. En dan heb je wel een laudatio vol. Ben ik dan nog wat vergeten? Wist ik zo niet. Dus we hebben een kleine enquête rondgedaan naast je collega's, promovendis op de afdeling. Kijken wat hun observaties waren. En dat wil ik kort samenvatten. Ik wil een paar observaties delen uit deze vragenronde. Kijken of ze ook vatbaar waren voor je werkvirus. Kernwoorden. Vraagbaak. Bron van kennis. En dan een herhaalde observatie. Pindakaas. En ik vraag me af, is dat dan het geheim? Gamer, danser, een hele schaarse observatie, drinker, nog schaarser, hoofdpijn. Ik heb niet allemaal meegemaakt met je, maar ik deel het graag. Beste Kevin, het was en het is een waar genoeg om met je samen te werken. Ik hoop dat ik nog heel lang met je samen mag werken. Heel hartelijk gefeliciteerd met de verkregen waardigheid. Draag hem waardig.
Dr. Groot Lipman, it is a pleasure for me to congratulate you on behalf of the university with this degree you received. Congratulations with that, congratulations to your family. And I really thank you for choosing this university to get your doctor's degree, because that means that for the rest of your life you are attached to this university. It's maybe the first time that you were in Maastricht, but still you're a doctor in Maastricht. Thank you for that, because it's always a pleasure to have good people connected to a university, and apparently you are a very esteemed already person. I have understood that is good for our university. I also thank Professor Kool, is she still present? Yes. Dr. Thewe, Dr. Vergeffen, for being present with this, at this ceremony. The other people are qualitate qua here, so they don't need a special thank. They are just professors here or doctors here, or at least they were already attached. I understand that you give a small reception afterwards, and we already thank you for that. I now switch to Dutch. No, one word in English still. Can Professor Kool and Professor Lambert stay on the screen until after the pictures made by the photographer, and I identified them there. So afterwards we make a small group picture here, but the people, and afterwards we make an official picture on the staircase in the hall for your office later. But then already Professor Lambert and Professor Kool have been wiped away by the technicians, and they are not present anymore. And now we switch really to Dutch. Mensen uit de zaal die kunnen alvast naar de receptieruimte gaan. Dat is een soort refter hier van die oude monniken die hier vroeger bivakkeerden, toen dit nog een klooster was. En daar treffen we u weer. Wij gaan dus die foto nog maken op de trap. Geliefden of mensen die om een of andere reden op die foto op mee willen staan, vaders, moeders of dergelijke, die moeten dan een beetje in de buurt blijven en de rest kan alvast aan een biertje beginnen en bitterbal, wat hebt u besteld? Zoiets. Maar wij doen dat fotowerk en intussen gaat u vast de zaal uit naar de receptieruimte. Dan krijgt u uw eerste drankje. Dan sluit ik na deze mededeling hiermee de academische zitting.
Recording stopped.
Dus wij gaan even hier staan.
Supervisors, would you like to join for the picture?